Alternate reality, could it really exist? Patrick Moore investigates now on BBC One in the Sky at Night.
Good evening. We are now going to go planet hunting, looking for planets of other stars and possibly life. But first of all, one news note. Several new moons of Saturn have been found. Two of them shown here. They're small and faint, but they are there. And Saturn has now more known moons than any other planet. So on now to our main theme. Our Sun is a star, a very ordinary star, and the centre of the planetary system, the solar system, which you can see there. And of these planets, much the largest and most massive is Jupiter. Giant Jupiter, a gas giant, can engulf over 1,000 Earths. I may say, look in the east now after dark, and there you will see Jupiter, shining very brightly, and Saturn is above and to the right of that. So Jupiter is large. Now, the stars are so far away, they appear only as tiny, twinkling points of light. Every speck of light there is a star. But even a big planet like Jupiter is very small compared with a star like the Sun. Therefore, how do we set about finding planets of other stars? There are various techniques. One I call the wobble technique. A massive planet going on a star will make that star wobble very slowly, very slightly, and that we can detect. Secondly, the transit technique. In our solar system, there are two planets, Mercury and Venus, closer in than we are, and therefore we see them sometimes passing in transit across the face of the Sun. There's Mercury doing just that. Venus will next do so in the year 2004. Now, supposing we have a star with a massive planet going around it, when that planet passes in front of the star, it will cut out some of the star's light, and the star will dim very slightly, and that we might be able to detect. Technique number 3, actually seeing a planet of another star, and so far we've not been able to do that. But the wobble technique has yielded results. Way back in 1995, two Swiss astronomers, Mayo and Quillars, studied a star called 51 Pegasi, near the square of Pegasus, you can see the naked eye, and there they found there is a massive planet larger than Jupiter going around it. And that was the first success. Other stars now studied, and by now we found over 50 extrasolar planets. And who better to tell us about them than Alan Penny. Alan, welcome back. So things are moving fast. What's the latest news?
Well, moving fast are the right words. At the Astronomical Union meeting in Manchester in August, 3 teams reported 9 new planets using the wobble technique. And a team using the Hubble telescope gave some beautiful results using the transit technique, which we'll talk about later. You know, the number of teams studying extrasolar planets is increasing all the time. The wobble technique is being extended to telescopes in the southern hemisphere, and in fact I'm a member of a team which is using the Anglo-Australian telescope with the wobble technique, and we're getting very precise measurements, so we're quite hopeful about getting some planets soon.
When you came on the program last, we were talking about the possible sighting of the spectrum of a planet going around a star called Tor Boötis, not far from the brilliant Arcturus in the sky. And that sounded very exciting, but I gather there are problems there.
Yes, we reported that we have been able to disentangle the planet light from the starlight in a very complicated way. We did have a slight caution. We thought there was a 5% chance that nature was fooling us, that we were seeing something that wasn't there. It's as though you're at a party, a very noisy party, and somebody said, the drinks are not ready, and you heard it, the drinks are ready.
Shame.
So there was this small possibility. So we went back to the William Herschel telescope earlier this year and observed some more, and the planet wasn't there. We're not quite finished the analysis, but if it stands up, we'll have to withdraw the claim. And of course, this is the way that science works. You say you've done something, another team, in this case our team, will check up on it, and if it's wrong, the claim's withdrawn. Science checks up on itself.
Scientists always check on themselves, as you say, unlike politicians, I may say. Presumably, all these techniques so far are limited to Jupiter-sized planets.
Yes, they're limited gas giants like Jupiter. For the wobble technique, the Earth is 300 times less massive, so the pull is very much less. And we can see the wobble technique working down to planets about the size of Jupiter, 19 times more massive than the Earth. And perhaps with techniques like the transit and another method called gravitational lens, with ground telescopes under special conditions, you might get down to just massive Earths, but it'd be very touchy.
Well, we really need telescopes in space. We have got Hubble, of course, but Hubble isn't geared for planet hunting. But the others are being planned. What about the successors to Hubble?
Yes, NASA and the European Space Agency, ESA, are together designing the follow-on to Hubble. It's going to be called the Next Generation Space Telescope, a rather boring name. But here's a picture of NGST, as we call it. It's 3 times larger than Hubble, and it's got a new feature. It's got a solar shield to shield it from the sun. That's the big blue object, and that makes it run cold. Now, NGST is going to be a wonderful telescope for astronomy, but unfortunately it's not going to be good for planet hunting. The trouble is, you've got this bright star next to the planet. It's like trying to see a glowworm perched on a searchlight. And NGST is going to be very good at looking for glowworms, but not for glowworms next to searchlights. For that we need a sort of special telescope.
Well, let's go through the various techniques, shall we? Beginning with the transit technique.
Yes, this is the technique which uses the light from the star. Here we have a simulation of a Jupiter going in front of a distant star, and you can see that as it goes in front it blocks out some of those lights. And in fact, all of the 50 planets which we know so far from the wobble technique have been searched using this technique, and this transit which I've just shown you is of one of those. This is the star HD 209458, and this is real data taken by my colleague Hans Dieg.
Well, the trouble is that when a planet goes around the star, it very often will pass above or below and won't go right across the star.
Yes, this is a good method if you know that there should be a transit. But if you're looking for planets by this method, you have to search thousands of stars. And in fact, the Hubble telescope has been used to look at the stars in the globular cluster 47-2 Tucanae, and although we expected to find some planets, it didn't find any. It seems so the stars in globular clusters don't have these close-in Jupiters.
But Hubble has had one success.
Yes, Hubble was used to look at that star where we know there's a transit, and it made an absolutely beautiful observation. It worked in a special mode and took very precise measurements. But of course, with the transit technique, we want to go down to Earths. And the trouble is Earths are small. You know, if we look at a picture of the size of the Earth compared with Jupiter, you can see it's really small. So if it was an Earth going around that star, the dip would be very small. And you could see that Hubble would just about do it, but it's not good for searching. So what we need is a telescope that can be as precise as the Hubble telescope, but that can search tens of thousands of stars.
And that leads on to 2 more missions now being planned, Corot and Eddington.
Yes, Corot is a French-European mission which has been funded for launch in 2004. And here's an artist's picture of it. This is going to look for large Earths close into stars. Now, that's going to be very exciting, but what we would really like to know is about Earths which are like Earth.
Right.
Earths which are warm, so there's liquid water on the surface.
Right, so.
And in our own solar system, the Earth is, of course, at that right distance. But if a star's fainter, the planet would have to be closer in, and if the star's brighter, it would have to be further out. And this diagram shows what it's like. The yellow line shows the comfy zone.
The habitable zone, in fact.
The habitable zone. And if we put the planets for our own solar system in, you can see that Earth is in the right place, but Venus is too hot, and Mars is too cold. So what we want is a telescope that can search for further out Earths. And for that, you need a larger telescope and a longer lifetime. And just last month, ESA decided that as long as its schedule permits, it would actually build such a telescope for launch in 2008. This is going to be the Eddington mission, and here's a picture from ESA, it's kindly supplied by Fabio Favata, who's the study scientist. And Eddington's going to be half the size of the Hubble, but only 2% of the cost, because it's designed in a very good way. And it's going to do other science as well, astroseismology. But starting in 2008, we're beginning to look for habitable Earths.
So within the next few years, we may find out there are habitable Earths there. But what are they going to be like?
Well, yeah, that's the next stage. Once we find they're there, we want to know what they're like. Are they like the Earth? And let's remind ourselves about the problem about actually taking a picture of an Earth going around a star. Here's a picture taken by the Hubble telescope of a very normal nearby star, Gliese 229. And that star's the large blob on the left.
Yeah.
And on the right there's a small blob, and this is a brown dwarf, a sort of failed star. Now this is actually much brighter than the planet. And if we put an Earth in this picture, it would be 50 times closer in and 1 million times fainter. It's a real problem. Now you could just block out the light from that central star using something called a chronograph. We could build a special telescope and put a chronograph on it. And this is the way a chronograph works. Here's a picture of a chronograph working in our own solar system. It's a picture from the SOHO satellite looking towards the sun, but that central disk has blocked out the sun.
Mm-hmm.
The sun would be just that small yellow circle in the middle, but you can see Saturn and Jupiter and Mercury directly. Now if we use this technique in this space telescope, we could do the same thing. And here's a simulation of a Jupiter round a nearby star. And in this version of the chronograph, it just dims the central star. But you can see it works quite well. But it's a big step from Jupiter's down to Earth's.
Well, what about other methods? I'm thinking of infrared and interferometry.
Yes, we think a better method will be using the infrared light rather than visible light. And the advantage here is that the planet is relatively much brighter in the infrared. Here's a plot of that effect. Along the bottom we've got wavelength, short optical on the left, long infrared on the right, and up the side we've got the brightness. And you can see the sun shining at the top.
Yes, indeed.
And down the bottom we've got the Earth. It's 1 billion times fainter. The scale's a log scale in brightness. But you can see on the right-hand side the Earth gets brighter. And this is because in the infrared we're not seeing the reflected light, but we're seeing the glow from the warm Earth. It's like a light bulb. A light bulb shines because it's hot, and the Earth glows because it's warm. So it's much easier to do in the infrared. But unfortunately you don't get something for nothing, and because you're using the long wavelength light, the telescope has to be bigger. In fact, it has to be 100 meters across, and building a 100-meter telescope in space is beyond us.
You could say that.
But you can use a technique called interferometry. In here you use normal, ordinary-sized telescopes. You take a few of them, spread them over 100 meters, join the light together, and together they work as well. Now, this is not a new technique. The radio astronomers have been using it for decades. And here's a picture of a very large array in New Mexico. 27 radio telescopes spread over a few kilometers are nearly as good as a giant radio telescope a few kilometers across. Both ESA and NASA have scheduled an interferometer in space for the year 2015 to use that technique. And here's a design study of the Darwin mission, as the ESA version is called, working in space. You've got 6 telescopes, each on separate spacecraft, joining the light together, and each telescope is sitting on a solar shield, just like NGST was. And then in the middle of those 6 telescopes there's a hub where the light comes together, and there's a lot of complicated optics inside that hub. And then with those telescopes and the hub, we've got an 8th spacecraft which will have the computers to control it. Now, of course, this is a really ambitious mission, but ESA is already starting the preparations, getting the technology ready. Just to take 2 examples, when we join the light together, we have to do it in a special way called nulling, which removes the central object, removes the light from the star. And ESA and the European Southern Observatory have agreed to test out the technology of this on the Very Large Telescope in Chile. And this is a project led by Malcolm Fridland, the Darwin study scientist. And another technology is flying these spacecraft around. And next month, ESA is going to decide how to use its SMART series of technology missions to do this.
Well, Darwin is certainly promising. It's also amazingly complex. Alan, how is it going to work?
Yes, we have to be sure that it's going to get good results. So we've done calculations of how it should perform. And here's a typical picture of what it will do looking at a nearby star. If that star had solar system planets around it, Venus, Earth and Mars, this is the picture you'd get back. You can see it's a bit strange. The interferometer has got some artifacts, but it has removed that central star, and you can see Venus, Earth and Mars quite clearly. I mean, they're blurred out, but we wouldn't see any detail anyway, even with a real 100-meter telescope. So we would be able to see them, and then of course we'll go on to study them, and we'll do this using spectroscopy. Spread the light out into its colours, and look for features at different wavelengths. Each chemical has a characteristic wavelength. It's like the way you know that inside a sodium street lamp there is sodium because it's got a characteristic yellow colour. And here are the spectra of the planets Venus, Earth and Mars in our own solar system. And you can see that Venus at the top, Mars at the bottom, have got a feature where you would expect carbon dioxide to have one. So we know there's carbon dioxide. And for Earth as well, we've got water and ozone. So even without visiting the solar system, you could tell that Earth is an interesting planet. And Darwin will do the same thing for these planets around the other stars. And here's a simulation of a spectrum we'll get back of an Earth, and you can see the features are there quite reasonably. So sometime about the year 2015, we'll be studying Earths around other planets.
Well, the most fascinating question of all, Alan, what about life?
Well, this actually is probably the most interesting part of Darwin, because if we go back to that spectrum of light, you can see the ozone feature. Now, ozone comes from oxygen, and oxygen comes from life. Grass and trees, bacteria in the ocean produce ozone, produce oxygen. So if you see ozone, you know there's life there. But what's the chance of there being life around on a planet? And the answer is we don't know.
Yeah.
And that's because we don't know how life started.
Right.
There is one small clue in that on the Earth, life started almost as soon as the Earth formed. It's almost as though life is an easy thing to do. And if that's true, then we've got a good chance of finding on nearby planets.
The trouble, of course, is that these experiments all lie some way ahead, and we really want to know. Can you give us any kind of a timetable?
Yeah, these large space missions take a long time to prepare.
Wow.
But we do have a sequence of missions, and here you can see them. 2004, the French East European mission to do the transits Corot, and then we hope we'll have Abington in 2008 to get those habitable Earths. 2009, NGST, the Large Telescope, which will be of some help to us, and then finally Darwin in 2015. But of course, not finally, because we're always dreaming. In the 2020s, perhaps we'll have the Planet Imager, which can actually take a picture of an Earth, but that's going to be a very future sky at night.
I wonder what they're like. After all, they must be there. Here's an impression by Tony Wilmot of a massive planet going around a star, and that could be duplicated many times in our galaxy, and I'm sure in other galaxies alone. We're on the threshold now of amazing new discoveries, and they're coming in thick and fast. And after all, only a few years ago, we had no idea that planets of other stars really existed. Alan, thank you very much.
Thank you.
Don't forget our Sky at Night website, www.bbc.co.uk/Sky at Night, and our CFAX, page 620. Next month, I'll be joined by Dr. Jeffrey Hoffman, one of the astronauts who repaired the Hubble Space Telescope. He's going to tell us about the sky as seen from space. And no one knows more about that than Jeffrey Hoffman does. So we'll see you then next month. Until then, good night.